This video is a lecture of Chapter 1 from the book of Statistics, Fundamentals of Statistics by Sullivan. In the first chapter, we're going to go over lots of definitions. So it might feel like I'm just reading a little bit to you. Obviously, you could read this on your own as well, but I'm going to also read it to you in this video as we go through these lecture notes. The definition of statistics is the science of collecting, organizing, summarizing, and analyzing information to draw conclusions or answer questions. In this particular book, we'll be going through all of the different categories of statistics. In the first two chapters, we'll be talking about ways to collect information and then how to organize it in the next chapters 3 and 4. How to summarize will be in chapters 5, 6, 7, and finally analyzing will be at the last half of the class. In addition to statistics, it is about providing a measure of confidence in your conclusion. So whatever you do with your analyzing of statistics, your conclusions that you're going to make are always going to have some sort of a confidence level associated with them. The information that's referred to in the definition is data. Data are a fact or a proposition that's used to draw a conclusion or make a decision. The data describes the characteristics of an individual. Data can be quantitative, qualitative, in other words, it could be measurable or just a categorical type of a data, but it describes something about that person or object. A key aspect of data is that it may vary. For example, is everybody in your class the same height? Obviously no. Does everybody have the same hair color? Obviously no. So among individuals, there is what we call variability. In fact, data vary when measured even on just ourselves. Of course, our height always stays the same as we get older, but do we sleep the same number of hours every night? No. Do you consume the same number of calories every day? No. So even within one person, sometimes our data can vary. Our goal in statistics is to describe and understand the sources of that variability. In other words, why do these characteristics change? An entire group to be studied is called the population. An individual is a person or an object that is a member of the population that is being studied, and a sample is a subset of the population being studied. For example, a population, let's say we're talking about the United States. So the population, if I could kind of draw the United States, okay? The population has over 300 million people inside of it. So over 300 million people would be the total population of this United States. One individual person that lives here in the state of Indiana is considered an individual. That could be you or me. Now, a sample is considered something that is a subset of the population, something that is smaller than the population. Usually it's more than just one person. So a sample might be everybody in the state of Indiana. This could be a sample. This could be a sample. The state of Florida could be a sample. The whole western part of the United States could be a sample. Just the city of Washington, D.C. could be a sample. So you can see that samples can be different sizes. They can be based off of geographical area, they could be based off of characteristics, or they could be completely sporadic. But each of these individual samples can be of different sizes. so sample sizes can vary. But the population size always stays the same. A statistic is a numerical summary that's based on that smaller sample. In the first half of the book, we will describe what is called descriptive statistics. In the descriptive statistics, we're going to be talking about how to organize lots of data, like collect that data, and how to organize it and summarize it so that it looks presentable. Descriptive statistics describe the data through numerical summaries, possibly tables and graphs. So this is going to be in the first half of the class. In the second half of the class, we're going to be talking about inferential statistics. Inferential statistics uses methods that take results from the sample that we've taken up here, but then we'll extend that to the population and measure the reliability of the result. A parameter is a numerical summary of the population. So what you're going to learn in this particular chapter is that in a population, being the whole country, we can try to take out what's called a parameter from there. A parameter might be, I don't know, the average age of the whole country. Clearly that would be very difficult given that there are over 300 million people in the country. So what we usually do in statistics is we find a smaller sample. Let's say everybody in the state of Indiana, or everybody in just one particular city or county. And we take all of them and we find out what their average age is. Clearly these two average ages may or may not be identical, but we're hoping that they'll be close. So if we can find a sample and find out what their average age is, well, then maybe we can suggest that that average age is what the average age of the whole country is, which is called inference. We would infer that this one small statistic is the same as what the parameter is of the whole population. Clearly, we can never be 100% sure of that. But how confident can we be? That's what inferential statistics is. We want to get as close as we can from a statistic about the whole population parameter, and how confident can we be that we are making that judgment. A couple of examples. Suppose that the percentage of all students on your campus who have a job is 84.9%. Is this a parameter or a statistic, and why? Now remember, a parameter comes from a population, which is everybody. A statistic comes from a sample, which is a smaller subset of the parameter. So again, suppose the percentage of all students, that's the key word there, is all students. All students indicates that this is a population, because we're talking about everybody on campus. And if we are suggesting that all students were surveyed and 84.9% of them have a job, then this would be a parameter, since it comes from the population. However, in this suggestion down here, it says suppose that a sample of 250 students is obtained. And from this sample, we find that 86.4% have a job. Is this a parameter or a statistic? Well, this would be a statistic, since 86.4% comes from a sample. And notice that these percentages are not the same. Remember, 84.9% of all students on Ivy Tech's campus have a job. But when we took a smaller sample or a subset of that, we found even more had a job. Well, we didn't really take a survey of everybody, so this number isn't going to exactly match. Turns out a higher percentage of our sample actually did have a job in our sample. The process to statistics is first to identify the research objective. In identifying what the objective is, this can clearly label what we need to do next. In identifying the research objective, the researcher must determine the question that they want answered. You're basically defining the problem. The question must be detailed so that it identifies the population that is to be studied. This is what we'll be doing in the first chapter. In the second, third, and fourth chapter, we'll start to collect the data and how we do that. Conducting research on an entire population is often difficult and expensive, so we typically look at a smaller sample. This step is vital to the statistical process because if the data is not collected correctly, the conclusions drawn can be meaningless. Do not overlook the importance of appropriate data collection. We will discuss this step in later sections. After we've collected the data, in Chapter 2 through 4 we'll start to describe that data. Descriptive statistics allows the researcher to obtain an overview of the data and can help determine the type of statistical methods that the researcher should use. We discuss this step in detail in Chapters 2 through 4. Then we perform the inference. Apply the appropriate techniques to extend the results obtained from the sample to the population and report the level of reliability or confidence of your results. We will discuss techniques in Chapters 5 through 8 and inferential techniques in 9 through 15. Some more definitions are variables. Variables are the characteristics of the individual within a population. A variable could be something like your hair color or your height. It's something that you can describe about a person or object. They'll be classified into two groups. We have qualitative data, which is just categorical, in other words, it's words, and quantitative data, which is measurable. Qualitative variables allow for just classification of the individual based on some sort of an attribute or characteristic, such as hair color. But quantitative provides a numerical measure of the individual. The values of a quantitative variable can be added, subtracted, and provide meaningful results, such as height. I can say, I am 2 inches taller than Mary. Here's some examples below. Are the following variables qualitative or quantitative? The first one is nationality. Nationality is a category, so that would be a qualitative data or variable. The number of children you have at home, that would be quantitative. I can numerically tell you how many children I have at home, and I can add and subtract those numbers and make a meaningful result. In other words, I have 2 more children than Joe. Household income would also be quantitative. It would be quantitative because household income is numerical. In addition to that, I can add and subtract data and make a meaningful result. I can say that I make $10,000 more than Mary. Level of education. Now, if we're talking about associate's degree, bachelor's degree, master's degree, and PhD, these are just categories. Even though they can be ranked, they're still qualitative in nature. I can't add and subtract those categories. Daily intake of whole grains. If we're talking about grams of whole grains, the number of grams that you're taking, this would be a quantitative data. I had 5 more grams than I did yesterday. Now, zip code is a tricky one. It's definitely numerical. However, can I add and subtract zip codes? No. My zip code, I do not explain a zip code as if I am 4 more higher than you are with your zip code. We don't add and subtract zip codes. Zip codes really are just a category. Even though they have numerical digits in its name, it's just a category or a listing of where you're located. We don't classify zip codes as actually being numerical data. So this actually will be qualitative. Quantitative variables can be further classified then as discrete or continuous. So each of these quantitative variables can be further classified even further into either being discrete or continuous. A discrete variable is a quantitative variable that has a countable number of possible values. A continuous variable is a quantitative variable that has an infinite number of possible values it can take on and can be measured to any desired level of accuracy. So remember, a discrete variable has a countable number of values, but a continuous variable has an infinite number of values. So let's look at a couple examples of that. These 3 examples are all quantitative data. This is all quantitative variables. The question is, are they discrete or are they continuous? Well, the number of children is countable. I can have 0 children, 1 children, 2 children, 3 children. That's a countable number of values. So this would be discrete. The number of cars that arrive at a McDonald's drive-thru between 12 and 1 p.m. That would also be discrete, because you could either have 0 cars, 1 car, 10 cars, 100 cars, but it is a countable value of number of cars. However, the distance that is traveled by a person in one single day would be continuous. And it would be continuous because you have infinite number of values in between the actual miles. For example, it doesn't take me exactly 9 miles to drive to work. It might take me 9.16384 miles. Tomorrow, if I go around the block, it takes me a slightly different amount of miles to get to work. It's continuous because in between each of the whole numbers on a number line, in between 0 to 1, 1 to 2, 2 to 3, and so on, there's also infinite number of possibilities in between those integers. Variables can also be measured in a number of other ways. Level of measurements called nominal, ordinal, interval, and ratio, starting from very basic to very descriptive. The very basic nominal level of measurement means that the values of the variable just simply have a name, a label, or their categories. In addition, the naming scheme does not allow for any ranking. So it's the very basic bottom level type of measurement. All of them would fit into nominal. The next step higher would be ordinal. It'd be the same as nominal, except for now this naming scheme allows for ranking. Interval. Same as above, but the differences of the values of the variable have meaning. A value of 0 in the interval level of measurement does not mean the absence of quantity. Addition and subtraction can be performed on values of the interval. Ratio. Same as above, and the value of the 0 in the ratio level of measurement means the absence of quantity. Multiplication division can be performed on the variables. So let's go through a couple of examples. And remember, anytime during these videos when you're asked to do something like this, I would always suggest you pause the video, try it on your own by reading the definitions first, then press play to see if you got them right. So what is the level of measurement? The number of snack and soft drink vending machines in the school. Well, everything starts at nominal. It definitely is a label or a category. However, Ordinal says I can rank. In other words, can I rank the number of soft drink machines? Well, of course I can. If there's 2 vending machines on this end of the school, there's 4 on the other end. I can rank them by size. Could it also be interval? In other words, can addition and subtraction be performed on the values? Absolutely. There are twice as many soft drink machines on the west end of the school than there are on the east. So this definitely is at least interval. Can it also be ratio? In other words, can multiplication and division be performed on the values? For example, if there are 10 machines on one end of the school and 5 machines on the other, can I divide those two values? Can I say that there are twice as many machines on the east end than there are on the west end? Absolutely. This would actually be a ratio level of measurement. It has an actual 0, meaning yes, there can be 0 machines in the school. And multiplication and division can be performed between different values, and it makes sense. Whether or not the school has a closed campus policy during lunch. This would just be a nominal measurement. There is no way we can rank our opinions. Your opinion that we should have a closed campus and your opinion, someone else's opinion that we have an open campus policy cannot be ranked. Those are opinions and they can't be ranked in any particular order. So ordinal is not possible. Class rank: freshman, sophomore, junior, senior. It literally says in the title that ranking is allowed. Certainly, they would be written in this order. They do have order to the categories. So this would be an ordinal level of measurement since there is order or ranking within the categories. However, it's not numerical, so we can't really subtract and add any sort of values in here. If it's numerical, it's usually saved for these last two categories. Temperature outside. Since it's numerical, we'll assume that it's going to be either interval or ratio. The question is, can I only add and subtract the data, or can I also multiply and divide? Well, let's look. Temperature outside. I certainly can add and subtract. I can say it's 10 degrees warmer today than it was yesterday. The value of 0 that's in the interval does actually not mean the absence of quantity. In other words, 0 temperature doesn't mean that there is no degrees outside. It doesn't mean we're absent of any temperature at all. It's just a 0 on the number scale. We actually have negative values. So 0 is just the middle, but we still can go below 0. Since we don't really have the absence of any quantity at 0, we definitely feel like we have interval. However, can we also have ratio? Can we multiply and divide temperatures? So for example, if it's 35 degrees out today and it's 70 degrees tomorrow, do I say tomorrow is twice as hot as today? No, this cannot be ratio. This is only considered interval. Since there is no true 0, 0 isn't the absence of quantity. There are negative values within temperature. 0 is not the starting point of our number line. You cannot say that 70 is twice as hot as 35 since 0 isn't the starting point. The number of cars that arrive at a McDonald's drive-thru. Now that would be ratio. It is ratio because I can multiply and divide those numbers. I can have twice as many cars tomorrow than I did today. 20 cars tomorrow is twice as many cars as there were today, which was only 10, for example. The distance traveled by a person in a single day. That would also be ratio for the same reasons stated above. If I traveled 12 miles to get to work today, but tomorrow I decided to take the scenic route and I traveled 24 miles, then taking the scenic route is twice as far, twice as many miles as it was when I took the straight route. Some more definitions. Into the next section, we're going to start talking about observations versus experiments. An observational study, we call it an observation for short, it measures the value of the response variable without attempting to influence the value of either the response or the explanatory variables. In other words, in observational study, the researcher observes the behavior of the individuals in the study without trying to influence the outcome. So think of yourself as looking through a darkened window where they can't see you, and you're just observing what is going on. You're not trying to influence the change by giving any type of vaccine or medication to try to alter what the outcome is going to be. You're just observing what is happening and writing down your results. However, in a designed experiment, if the researcher assigns the individuals in the study to a certain group, intentionally changes the value of that explanatory variable, and then records the value of what was the response for each group, then we're conducting what's called the designed experiment. For example, let's say a flu shot was given for seniors, and we looked at the records of 36,000 different seniors aged 10 for 10 years. And then we divided into two groups, those who got the flu shot and those who do not. It was determined that seniors who got flu shots were 27% less likely to be hospitalized for pneumonia or flu and 48% less likely to die for pneumonia or the flu. This is an example of an observation. We didn't actually give the actual vaccination. We just looked back on time over the last 10 years and observed what was happening. So this is an observational study. This is a good time that I'd like to go through different observations and experiments. In your book on page 19, we have a lot of really good examples of observations and studies. Number 9, we talk about the American Cancer Society, and it's beginning a study to learn why some people never get cancer. In order to take part in the study, a person must be 30 to 65 years of age and never had cancer. The study requires that the participants fill out the survey about their health and habits and give blood samples and waist measurements. These survey results must be filled out every 2 years. The study is expected to last for the next 20 years. This is an example of an observational study, and it's an observation because no change took place. The researcher did not invoke any change upon these participants, they simply just watched them over time. However, number 10 is an experiment. Rats with cancer are divided into two groups. One group would receive 5 milligrams of a medication that is thought to fight cancer, and the other receives 10 milligrams. So you have two different groups here. One group's getting lesser amount of medication, and one group's receiving more medication. And after 2 years, the spread of the cancer is measured. This would be an experiment because the researcher is invoking a change specifically to 2 different groups to try to see if there's a difference in the medication and the difference of the results. So the researcher is actually intervening and creating some sort of a change within the variables themselves. Questions 11, 12, 13, 14, 15, and 16, all the way through number 16, are really good examples that I would suggest you read on your own when you have time. These are all in your book. It is my page 19, but it might be a different page in your book. It is the last page of section, it's the questions from section 1.2. So moving on, now we're going to talk about what are some possible issues that you can see within an observation. Confounding. Confounding occurs when a study, if the effects of 2 or more explanatory variables are not separated. Therefore, any relation that may exist between the explanatory and the response may be due to some other variable or not accounted for in the study. For example, let's say you got the flu and you gave yourself, in order to treat the flu, you gave yourself some ibuprofen, but you also gave yourself some over-the-counter Walgreens Sudafed type of medication. And you gave yourself both. And then you felt better. How do you know which one of those 2 drugs was the actual explanatory variable that caused the response of you to feel better? We wouldn't know. That's what confounding is. In order to not create confounding, you always want to introduce one thing at a time, see what the response is, then introduce the other variable. A lurking variable is an explanatory variable that was not considered in the study. In other words, you didn't really administer it, but it was there all along. You just didn't think about it. But it still affects the value of the response in the study. In addition, these lurking variables are typically related to the explanatory variable that are considered in the study. A good example of a lurking variable would be if we wanted to see whether or not 2 things were related, which we'll get to later in chapter 4. So for example, let's say crime is highly related to temperature. Is highly related to ice cream sales. And as crime goes up, so do ice cream sales. Or as ice cream sales go up, so does the amount of crime that is happening within a city. You can see that these are positively related. Well, clearly, ice cream sales is not causing crime to increase. There is what we call a lurking variable in place. In here, the lurking variable would be temperature. Temperature is what is the lurking variable that is associated with both of these topics. Clearly, when the temperature gets hotter, ice cream sales goes up. Also, when the temperature gets hotter, crime increases because more people are loitering outside. So temperature in this case would be the lurking variable. Ice cream sales and crime are not necessarily really related, but temperature, the lurking variable, is related to both of them independently, and they have that in common. The big difference between confounding and lurking variables is that lurking variables are not really considered in the study, whereas confounding variables are actually measured. So think to yourself, what are some confounding and lurking variables that might have been at play back here in the flu study? For example, I'd like you to think of what are some ways that confounding or lurking variables might have been used. Now is a good time to pause and think about this. Confounding variables could be, was the shot administered every year? Was it consistent? In other words, if you gave the shot every year or every 6 months in 1 year, could be different than the next year giving it only every 2 years. So make sure that that was consistent. Otherwise, you're confounding two different types of administration. Lurking variables could be the characteristics of the specimen itself, such as age, maybe the health of the specimen before the flu. Were they well before, or were they sick before? And maybe even socioeconomic status. Things you obviously can't control, but definitely could be lurking variables within your study. Lastly, it is very important to notice that observational studies do not allow the researcher to claim causation, only association. A great example is up here. Ice cream sales do not cause crime to go up. Temperature does not cause crime to go up. They are only associated. We cannot say that one causes the other to happen unless we actually invoke a change in an experiment like a medication. If you take a medication and the response happens, we can say that that ibuprofen caused a reaction. But in this example over here, this was just an observation. We can only say that these two characteristics are associated to each other, not caused. To finish out section 1.2, I'd like to finish talking about the different types of studies. These are observations, and the three types of observations we'll be referring to. A cross-sectional study is an observation that collects information about individuals at specific points in time or over a very short period of time. A case-controlled study is retrospective, meaning that they require individuals to go back in time and require the researcher to look at existing records. In a case-controlled study, individuals who have certain characteristics are usually matched with those who do not. In a cohort study first identifies the group of individuals to participate in the study. The cohort, which is the people or individuals participating in the study, are observed over a long period of time. And over this time period, characteristics about the individuals are then recorded. Because the data is recorded over time, the cohorts are prospective. So case control looks back in time. Prospective takes them and goes into the future with them. And cross-sectional is a very short amount of time. Let me read you a couple of examples of each of these. First, I'm going to read you an example of a cross-sectional study. A cross-sectional study would be similar to the example that I read a little bit earlier in this lesson. It is number 19 from section 1.2. This example here. In other words, is a television in the bedroom associated with obesity? Researchers questioned 379 bedroom-associated 12-year-olds, adolescents, and concluded that the body mass index of those adolescents who had a TV in their bedroom were significantly higher than the BMI of those who do not have a TV in their bedroom. This is considered an observational study that is cross-sectional. Now remember, a cross-sectional study is an observation that collects information about an individual at one specific point in time or a very short point in time. And that's what this is. We went out and asked 379 12-year-olds a particular question. Right now, at this moment, do you have a TV in your room? We weren't watching them in the past or watching them in the future. It was just the question about right now, what cross-sectionally, he basically took a knife through the timeline and said, right now, today, do you have a TV? And if the answer was yes or no, we were able to determine what their BMIs were based on whether they had a TV or didn't. So this was a cross-sectional study. Let's look at an example of a case-controlled study. A case-controlled study. An example of a case-controlled study would be right here. What if we match individuals who smoke with those who do not? When we say match individuals, we mean that we would like the individuals in the study to be as similar or homogeneous as possible in terms of demographics and other variables that may affect the response. Once homogeneous groups are established, we would ask that the individuals in each group how much they smoked over the past 25 years. The rate of lung cancer between the two groups would then be compared. Now this is called a case-controlled study because in this study the information was retrospective, meaning that they required individuals to look back in time or required the researcher to look at old existing records. The last type of study is the cohort. The cohort, an example of that one, would be number 17 in your book, which is from section 1.2. This would be an example of a good cohort. Is there an association between level of happiness and the risk of heart disease? Researchers studied 1,739 people over a 10-year period and asked the question about their daily lives and hassles that they face. The researchers also determined which individuals in the study experienced any type of heart disease, and after their analysis, they concluded that the happy individuals are less likely to experience heart disease. This is an example of a cohort because it's prospective. The cohort first identified the type of groups of individuals that were participating, then we observed them over a long period of time. We basically were finding groups with similar demographics and then we asked the questions. To finish up section 1.2, we lastly have to talk about what the definition of a census is. A census is a list of all the individuals in a population along with all of their characteristics. A census could be a census of the total population of the United States. So for example, every so many years, I think it's every 10 years, the United States comes out with a census and they try to do a mailing to every household in the country to get back information on what the average age and income and ethnicities are of all of the households. Clearly they're not going to reach everybody and not everybody's going to respond, but it is an attempt to reach everybody. A census is a list of all of the individuals in a population and all of those characteristics.